Hi. So we were looking at the energy equation, right? And what we basically started out doing is by saying that the 2D steady state energy equation, right, is given by 1 here and 2 here. Okay, so and is basically if I were to look at this equation on the left hand side, so this is the change in internal energy, right, left hand side of this equation here, so change in internal energy, right, and you can see that this is like the convective change in the temperature, right. So del T, del X, del T, del Y, right, and U and V are the velocity components. Now, and this term, and Cp is the isobaric coefficient of pressure, which we've defined earlier. Now, this internal change in internal energy, which is essentially the convective change in temperature, can be written in terms of the term which contains lambda as well as this phi, and the phi looks something as given in equation 2 here, right. And this, so essentially we have a conduction term and a dissipation term, right. So because lambda is essentially thermal conductivity, right, and phi is the dissipation function, which is given in 2, right. And so we went ahead, so this is the form of a 2D steady state energy equation. So we started out with the conventional energy equation, saying that rate of change of total energy is equal to heat flux plus power, and we went ahead and looked at a fluid element and saw how we could get the equation now. So we finally did all these calculations, and we came upon this expression and this expression, right. Once we came upon this, right, and also, so therefore using 1, 2 and the expression this, right, we basically, if we solve this, right, we should be able to get 1 and 2, which is the 2D steady state energy equation, right. And now so now the details of these derivations is something that I will post on the web page, so you can take a look at that. And of course, I would definitely suggest that go through it, do this yourself. It always helps for better understanding. Now, so that's where we kind of stopped earlier, right? Now, so of course, as we have seen here that in order to solve for the temperature, right? So we will basically need a we need to basically know the velocity field, right? Now, if you look at this equation, right. So this is our equation, and we said that the total change in internal energy, which is the left hand side, right. Now that can be written as the conduction term, right, and the dissipation term. So, however, the dissipation term, definitely you can see that that has a definition of the velocity. Therefore, in order to get in order to get the thermal field in this particular case, we need to know the velocity field. Okay, so let me jot down a few points for you. Okay, so let me jot down a few inferences that we made so far, right? So in equation 1, so let's say. Okay, so okay, now in equation 1, okay, the left hand side, right, left hand side is the change in internal energy okay, which is essentially convective change in temperature. Okay, and this is basically possible to evaluate. Okay, possible to evaluate the above in terms of conduction and dissipation. Right. So, so essentially now the point is that we need to know the velocity field. So, okay, so therefore, let us see how if we can, so, we could probably write this down as we've done earlier, right, using non-dimensionalized quantities. So, let us see how we will kind of do that, right. So, let us consider non-dimensional properties. Okay, so if I do that, let us use these, and well, we will assume a high Reynolds number for this case, so that the flow will have boundary layer character. Okay, and we will use the following non-dimensional quantities using. These are similar to what we've been doing so far. Non-dimensionalized quantities, right, which is x star, right, right, then theta right. Now, this is delta T is basically some suitable temperature difference. Now, what we've seen earlier that it could be the wall temperature, the difference between the wall temperature and the free steam temperature, right? That's a possibility, but it's essentially whatever is suitable, to the problem at hand. Okay, this and again y bar, right, and v bar. This, okay. Now then, okay, so basically equation 1, then we can write the steady state 2D energy equation as follows, right. So then we shall write it as rho Cp V by L delta T, okay, into, let's write this in a, just to, okay, give me a sec. Okay, this is taking way too long today. Okay. Okay, so U star del theta del x star plus V bar del theta del y bar. Okay, is equal to lambda delta T by L square I'm just trying to pinpoint where we're using this theta, because that's what we're interested in. We're really interested in the temperature flow field, right? So del 2 theta del x star 2 plus RE del 2 theta that, right? This then plus, okay? Okay, plus nu v square by L, okay, 2 plus okay, now this time I'm going to write this out, 1 by RE del V bar del X star by okay, and well, here too. So then this is del U star del X star square plus del V bar del Y bar square. Okay. Now, the detailed derivation of this is something that you can, look at. Well, I will basically post it. Okay. So then, this is essentially, this is equation 10. Okay. Now, this is equation 10, and so basically we're writing the 2D steady state energy equation in several forms. So here, as you can see, that instead of the temperature, right, so we said we need the velocity field, and what we do is we write this down. We did have the, this in terms of the temperature, right, as the convective change in temperature, and what we've used now, the usual non-dimensional variables, and we are able to get something like this, where what we have essentially is the non-dimensionalized temperature theta, right? Non-dimensionalized temperature theta. Okay. Now, if I do that, now what we'll do is since we said this is going to be at high Reynolds number, so that we have the boundary layer behavior, so that we are able to see boundary layer behavior. So we're going to take this for the limit. So for this, right, then this 10 equation, you can see it becomes so and so. Then it becomes, okay, U star del theta del X star plus V bar del theta del Y bar, okay, is equal to 1 by PR. This is the Prandtl number actually. I'm going to write it down for you. Del U star del Y bar, this, right? So essentially, if I say that Reynolds number is very high, then we're looking at each term. And this is something that we've done earlier, and I would like you to sort of go through each term and make sure that you agree with what I have written, right? So, I think you should be able to do that. So at high Reynolds number, what happens? Okay. So we write it, in this way, where PR, right, is the Prandtl number, which is nu Cp by thermal conductivity, right, and the Eckert number, which is V square by Cp into delta T, right. So, of course, here if you have this equation, so this is now an important equation for us, okay. So, this is an important equation for us, and right, this is equation 11, right. And of course, here this equation will have to assume that at high Reynolds numbers, the Prandtl number, right, and the Eckert number are finite values, right, that they don't blow up or anything. So, that is essentially, so this kind of, well, we assume okay, that the Prandtl number and Eckert number are finite at large Reynolds numbers, right. Now, a Prandtl number actually is a pure physical property, and what I will do now is give you, just a feel for the kind of, the type, so I will give you some of the, typical values of the Prandtl number. Okay, so the Prandtl number, okay, is a right. So, it is a pure physical property, meaning it is a property of the fluid itself, right. It is not something that comes on and off due to the fluid flow, right, but it is a property of the fluid itself. So, it is a pure physical property, okay. And so, if for example, let us write here. Okay, so this is the Prandtl number. Okay, I will write it for various cases. Now, this is T degree centigrade. Okay, so I got at 20, at 200, and at 500 degrees. Okay, this is for air. This is for air, and the Prandtl number for 20, for example, is 0.717, at 200 is 702, and for 500 is 0.696, which is interesting, right. If you look at that, with increase in temperature, the Prandtl number decreases from what I can see from here, right. Again, so you got temperature, and this is Prandtl, I mean this is for water, okay. This is for water, and this is at 0, okay. This is very interesting, 13.47. I got 20, which is 7, and I got 70, I got 2.55, right. Again, and this is for oil. Okay, so this is 0, okay, 1303.6. Okay, for 20, it is 412.28, and for 70, it is 80.35. right? Now, what is interesting is, see, you can make your inferences from here. So, if you see, if I were to compare, let's just say that, just between water and oil. Now, water and oil are both way more viscous than air, right? Viscous than air, and also the density is way more heavier, right? The density of water and oil is much larger than that of air. So, what you see is, for at least water and oil, that in here too, with increase in temperature, this is Prandtl number, okay? This is Prandtl number. This tabulation is for Prandtl number. Now, for all water, air, water as well as oil, with increase in temperature, the Prandtl number decreases, right? Increase in temperature is decrease, that I can see, right? Now, oil is more, denser than water, and you can see that this is almost 100 times more than the Prandtl number is almost 100 times more, right, than water, right? Now, what you can see here, the Prandtl number is got the coefficient of viscosity here, so that kind of gives you a hint right away, right? So it is directly proportional to the coefficient of viscosity. So obviously this is way more viscous. So this is almost like 100 times more than that of water. So again, at 0 degrees, as you increase 20 degrees, then this is 412. So again, it is more than that of water at the same temperature, and it is more than that. Now, for air, you see that even for 20 degrees, okay, you can compare the 20 degrees, it is extremely less, it is 0.7, right? So if you go up to 500, then you kind of, decrease, you decrease the temperature. If you go up to 500, then you get around 0.7, right, which is nowhere even like, close. So if you are at 20 degrees, so then you get like 0.7. Okay, so definitely, I mean, that's kind of, so that's what we can see. So of course, it is a direct, Prandtl number is directly proportional to the coefficient of viscosity, hence we see this, okay. Now, the Eckert number, of course, is a measure of the dissipation effects, okay, dissipation effects, and as you can see that this grows, okay, as a square of the velocity, which means that for very small velocities, you can neglect this, right? We can neglect this. For example, again, air is like, seems to be this spoil sport, so to speak, okay? So now, for example, for air, right? Okay, let's change that. Now, okay, now for air, okay, Cp is 1000 meter square per second square Kelvin. V is equal to 10 meters per second. Delta T is 10 Kelvin, and Eckert number is 1 by 100 basically, right? Now, well, essentially because of the dissipation, therefore, okay. So because of the dissipation, there is no heat transfer, but there is a temperature field which emerges because of that, right? And an example for that could be insulating walls, which are adiabatic in nature. So of course, the walls have higher temperature, right, than the outer wall, than the outer surrounding fluid, which is a free stream, T to infinity, and this is something that we call as adiabatic wall temperature. Okay, now we know right, we know that at the edge of the boundary layer, right, that is at y is equal to delta, right, is 0, right. So, now if that is so, right, del u star del y bar, okay. So, which means that the term containing the Eckert number, right, which is here, which is basically the dissipation term, right, in equation 11 if you see. So, that is going to go off, right. So, therefore, we will be left with this equation, right, which is only in theta, right. Now, so therefore, a possible solution, okay, so a possible solution is for 11 is theta is equal to 0, right, and theta is 0, right. So, which means what? Theta is defined as t minus t infinity by delta t. That is what I have defined. So, if theta is 0, this implies that t is this, right, which means that at large distances away from the wall, right. So, at large distances away from the wall, the temperature of the boundary layer, right, boundary layer edge is basically is equal to the free stream temperature, right. So, in other words, theta is a function of x star y bar, which in this case is far away, right, and the Prandtl number, and that is equal to 0, right. Now, equation 1, right, which we have seen earlier. So, mathematically equation 1 is a linear differential equation, right. It is a linear differential equation which has the standard solution theta, right, which is x star y bar Prandtl number Eckert number. This is what it depends on. So, it has a standard solution theta 1, which is x star y bar Prandtl number, okay, plus Eckert number into theta 2 x star y bar and Prandtl number. Okay. This is Prandtl number. Now, which essentially means that we are, so theta 1, as you can see, we have the theta 1, right. So, this is a solution which does not contain the dissipation, which does not contain any dissipation, and the second term, which contains the Eckert number, essentially contains the dissipation, right. So, right. So, this is your equation 10 and 11, okay, and so, right. So, this is general solution to the equation 1, okay, yeah. So, okay, so equation 11. So, now, so therefore, let us see that this essentially is, if I may clarify here, that this is a superposition, right, of theta 1, right, which is solution without the dissipation, right, plus theta 2, which is solution with dissipation, right. So, then we can write, therefore, we can write the solution, therefore, we can write the equation 1, therefore, we can break it down, and what we can write is this. So, we will break that down in terms of theta 1 and theta 2, right, del x plus v bar del theta 1 del y bar is equal to 1 by Prandtl number del 2 theta 1. Right? These are nice, equations which we can write and plus this is the equation which has the dissipation effects. Okay, so when I write that, right, so this is equation 12. Okay, so now 12 and 13 can be investigated separately. Okay, so essentially what we're doing is we're breaking down equation 1, right, into 2 equations, which is easier to solve, or basically it's a solution of the linear differential equation where we define these 2 functions, theta 1 and theta 2, which is essentially solution without dissipation and with dissipation, right. Now, so the way we can look at equation 12 is that in here, this is a linear equation. The dissipation term, this holds. Why? Because the dissipation terms are small, right? The dissipation term is small, dissipation effects are small because the velocities are small, right? And since this is, so therefore the Eckert number is basically negligible, it's say nearly 0. And this is a linear equation, it's not a problem. So if I want to solve that, all I need to do is just add back the dissipation term, right? So, so therefore, it basically breaks down to 12 and 13, and you can see that this is an easy equation to solve from, the equation that we started with, which was 1 and 2. Okay, so so therefore, I think we'll close here, and some of the detailed derivations is something that I will post for you, and you can take a look at this. So we have come up with equations in order to solve for the thermal boundary layer. Okay, so we'll stop here and move on to new things in the next model. Thank you.